Now you might be asking that why the sorting is being taught in the class of trees. Obviously, this may have been taught in the last chapter, but this is important because of the fact that heap sort requires to be done in the form of a heap tree. Therefore, what we have to do is that we have to know that what is a tree, what's a heap tree, and therefore from the heap tree only I'll be able to perform the heap sort. Now this sorting algorithm is a very good algorithm because it has the best time complexity of order of L log n. Therefore the complexity of order of n log n, and you know that algorithms which are having complexity of n log n are considered to be the best algorithms if it is based on comparisons. Okay. Now, before we start with the heap sorting, let me first of all tell you what is a heap. What's a heap tree? The property of a heap tree is that it is always a complete binary tree. That means at no point of time it will ever become a non-complete binary tree. And you know by definition, complete binary tree are that tree where except the last level, all the levels are having the maximum number of nodes. And even at the last level, the nodes must be pushed to the maximum left. Okay, that is the basic definition of a complete binary tree. Now, second thing is that the root is bigger or smaller than its. That means the root is always either bigger or smaller than its children. Now, why I wrote oblique? Because I might have a tree where the root is always bigger than all its children. And similarly, there could be another tree where the root is always smaller than all its children. That means any one of them will be true, but you will not have a tree where some root is bigger than its children and some root are smaller than the children. And of course, you know that this definition is recursive. That means it should be for at all levels, starting from the root to the last level. This definition should hold, and therefore such a tree is called a heap tree. Now, the question is how we are going to implement the heap tree in memory. Obviously, you know there are two ways to do. One is a linked list method, and second is a array method. Now, since we know that if I am going to maintain a heap tree as an array, there will be no spaces which are there in the middle which will remain vacant. Therefore, all the nodes will be put into an array in a continuous manner, and you have been told that the left child is always put at the 2 into I, and the right child is put into 2 into I plus 1, where I is the index of the parent. Okay, that means I will have a tree which will be like this, or maybe I will have a tree which will be like this. Now this tree is a heap tree by first property, but by the second property you have to put the data in such a way that this should not violate the heap property. Now what I can put the numbers. Maybe if I am going to make a heap tree where the root is bigger, I might put say 80 over here, maybe 60, maybe 75, maybe 40, 30, 20, 10. You might put 32, you might put 64. And if you check the second property, at all levels, the root is bigger than its children. The root is always bigger than its children. And therefore, by this property, this is a heap tree. Since the root is the maximum, therefore it is called the max heap tree. It's called the max heap tree. Now this tree is a max heap. If the root would have been smaller, it would have been called a mean heap tree. Now that is a basic difference between max heap and a mean heap. In a mean heap, you create a tree such that the root is smaller than all its children, and this definition will recursively hold. Now if you are going to use this tree, this will be a max heap tree. Okay. Now the question is how to maintain the memory. Obviously, you can maintain as an array. Where this is of 1, and you are going to put the first number at this place. The left child will put at 2 into I. Therefore, you are going to put the left child at this place and the right child at this place. Similarly, the left child 40 will be put in the 2 into I position of 60. That is 2 into 2 is 4. Therefore, you put 40, 30. Similarly, 32, 64. And you will put 20 and 10. And this is how you are going to put the elements in an array. Now, one thing what you saw over here is that there are no spaces in between which are empty. Why? Because since it's a complete binary tree, the array will always will always have continuous elements. Any space which will be empty will always be at the end. And therefore, if I am going to put a number, the new number, I will have to put in the left of 30 only. I have to put only in the left of 30. At any other place, if you put that number, it will violate the property number 1. We say that it should always be a complete binary tree. And by this method, it's very clear that when I am going to make a heap tree, it has to be a complete binary tree with the particular properties. Okay. Now, if I am going to use this tree for say sorting, what should I do? So let's try to make a mini tree. Now, example of maybe this is a example of a mean heap tree where the root is always smaller than all its children, and therefore this is a mean heap tree. Now the question is, where will you maintain a min heap or where do you maintain a max heap? The choice is simple. If you are going to perform a sorting in ascending order, make a min heap tree. If you are going to perform a sorting in descending order, make a max heap tree. Therefore, if I am having a number and I have to create a ascending order, I'm going to sort those numbers in ascending order. Obviously, I will use a min heap tree. Now, if you find the root is the smallest of all, now since this differential is recursive, what happens is that the root is smaller than all the children. Similarly, at the next level, 50 is smaller than all 60, 70, and 120. Similarly, 45 is smaller than 82 and 80. Now, one thing you should be very clear that 60 could have been on the left also, on the right also. Therefore, don't confuse. This is all. This could have been like this also, or maybe I could have put like this also. Fine, this is also correct. Therefore, don't worry about the placement that a left hand side is smaller, right hand side is bigger, nothing like that. Now, if you see, left of 50 is small, bigger than right of 50. Similarly, 45, left of 50 is smaller than right of 45. Therefore, obviously, there is no such rules like a smaller, bigger. The only thing is that the root is always bigger than all its children or smaller than all its children. And this is the example. Now, the question comes, how to build a heap tree? Now, here, how now obviously, if you are going to build a heap tree, the numbers will come one by one. Okay. Now, let us take an example that the numbers I have is say 40, 28, 60, say 47, 10, and say 90. Now let's take this. I want to make a heap tree with this. Now, what type of heap tree you want to make? You want to make a max heap tree or a min heap tree. Now, this will be totally same, except that at one point of time there will be difference between a max and a min heap tree. Now, if I am going to take this, what you have to do is start with the first thing. At the step number 1, you are going to put a node 40. Obviously, it is a complete binary tree, and of course, it is the bigger than all its children, and there are no children. It is biggest. Now, after step 2, at step 2, I am going to put say 28. I'll put this at this place. Again, you find that it's a complete binary tree. And of course, it's a max heap, the 40 is bigger than the 28. And also, this is perfectly valid because you are going to make a max heap tree. Okay. Now, here I am going to make a max heap tree. Now, come to the step number 3. I will have 60. That means step 3. You had this. And you have to now insert 60. Now, to insert 60, you have only one way, and this you are going to insert. Now once I insert 60, the first property is perfect because in this case it's a complete binary tree. But the second property is violated because now the root is not bigger than the left, not bigger than it or its children. Therefore, in that case, it is not a heap right now because you have violated the second property. Now, what to do is that you have to compare 60 with 40 and you find that 60 is bigger, therefore you have to swap the numbers. Now, in that case, you have to swap. To swap these numbers. And when you are going to swap this number, you are going to get this tree. Now this is perfect. This is a binary. This is a complete binary tree as well as a heap tree. Okay. Now take the fourth number. The fourth number is 47, 10, 90. The fourth number you are going to take for the step. It is 47. Therefore, you have to put here. Again, you find the properties violated between 28 and 47 because at that time 47 should not come here. Then what I am going to do, I am going to swap these two, and I am getting a tree which will be like this. And this is now perfect. Now, the fifth step, I am going to put 1090. Therefore, in that case, you are going to put a step 5. You will just bring this. And now you have to put 10. So you put 10 over here. Now when you put 10, nothing has to be done because the property is not violated. Now the last step is step 6. And you have to put, say, over here 60. And then you have to put 90. Now once you put 90, you find that the property is violated. And now you have to swap 90 with 40. Then what I am going to do is that you are going to swap this one with this one. And what you get after swapping, after swap, you are getting this one. And you get this. But again you find that even this is not a heap tree because 90 is bigger than 60, which should not be there. Because in the now again what you have to do is that you have to again make a swap. Therefore you have to swap this with this. Because now again it is not there. Therefore what I am going to do, I am going to again perform a swap. And after swapping, you find that now this is a perfect heap tree. And this is now a heap tree.
Excuse me, sir.
Ah,
Sir, in heap, sir, in fourth step, sir, we can put 28 with 40 also.
28 with?
40 as
No.
its children.
See, you have to make a tree in such a way that every time it should be a complete binary tree. And when you want to make a complete binary tree, it has to be put at a position, so it has to be the leftmost position. You cannot put at any other place. If you are going to put at any other place, it will violate the property number one, which says that every time the tree must be a complete binary tree. Okay?
That means for the complete binary tree, the tree must, the children must be at the leftmost, no?
All the levels except the last level, except possibly the last level, must be having the maximum number of nodes. That means at the first level you should have 2 power 0 nodes. At the second level it should be 2 to power 1, 2 to power 2, 2 to power 3. At the last level, if it is not full, it should have the node pushed to the maximum left. Okay. Now, one of you have written that we can sort the array and then easily make the tree instead of swapping at every insertion. Of course, this is a way out, but that is when you are going to sort an array, it will always be an n log n. It will always be an n log n or an n square algorithm. Therefore, that is one other sorting algorithm. You can do that, but this is another way to maintain an algorithm. Now, you might know that there are a lot of algorithms which are having an n log n complexity. Therefore, one of them is a heap sort. Of course, there is a merge sort also, which is having an n log n. Now, quick sort, you know that it might not always become an n log n. It might become an n square algorithm as in one case. All the insertion sort, bubble sort, then selection sort are all n square algorithms, and n square algorithms are not considered the good algorithm. Now the better part, the best part of this algorithm, heap sort will never give you an order bigger than n log n. Therefore, at any point of time, it will be not n log n algorithm, and n log n are the good are the best algorithm. Therefore, we have to do all those algorithms which are of order of n log n. Okay. Therefore, now here when I get this tree, the question is how to get the sorting algorithm. Now this is therefore this step is called a build heap step. It's called a build heap step, where you are going to build a tree. Now tell me, now then when what will we do with the heap tree? Okay, we'll just come to your question, Vithan. What you're asking is that what will you do with the heap tree? Now, in that case, we are going to convert this heap tree into a heap sort algorithm. Now, let us try to analyze the complexity of this. Now, what is the complexity of this build heap? Okay, I got it. Now tell me how to calculate the complexity of this build heap. Obviously, now let us try to come from a very basic beginning. When you inserted the first node, how much time it took? That means for the first node, it took order of 1. For the second node, it again took order of 1. For the third node, it will take order of 1. That is only talking about insertion. Okay. Why I am saying this? Even for the nth node, how much time it is going to take? Any question? Any? Okay, will you agree with me? It will take order of 1 only.
How, sir? We need to transfer sir to that node.
No, I'm not talking about transfer. I'm just talking about insertion. Because you are inserting in a heap. And heap are basically maintained as an array. Now let us try to understand this concept. Okay, now this is an array. Actually, we are not going to maintain an tree as a tree. We are going to maintain a tree as an array because tree are not stored in memory directly. You can only store a tree either as an array or as a linked list. There is no tree which is stored as a picture. Okay, therefore, basically, trees are stored as an array, or you can store it as a linked list. Now, in this case, when you find over here, the first number was 90. Therefore, it will be stored something like this. Okay, now let's check these numbers. 90, 47, 60, 28, 10, 40, and this will be stored like this. Now, if I want to store the, say the next element, now obviously you know that if I am going to store the next element, I will store it at this place. Maybe if I want to store, say 55. Or 65 or 75 or 85, whatever number, that doesn't make a difference. Now, if I can want to insert the numbers, I know that the next position which is now empty, back end is 7. Therefore, I will store at this position. Because I will maintain an index where I have to put the new number. How much time it took? Only order of 1. Because every time I am going to use a pointer which will point to the next free position. Now, when I'm inserted at 55, I will put the position of, maybe I'll put a value, say I, which will point to 8. That means anything I want to put as a new number will be put at 8. And therefore, all these insertions will take only an order of 1 time. Now, this is just to make sure that to insert. But the second thing is that you have to again perform the swappings. Okay. Now this is the first. This is for only for insertion. Now the second is to swapping. Now let us try to see the worst case. The first node does not require any swapping. The first node, when you are going to insert, will not require any swapping. That means the number of swaps will be only 0. For the second node, you require maximum 1 swap. For the third node, also you require only maximum one swap. For the fourth node, you require maximum of 2 swaps. For the fifth node, you require maximum of 2 swaps. And for the nth node, how much number of swaps you require?
N by 2.
N by 2. No, it's wrong. You can just see this from top. You can get by n by 2, but that's the wrong answer. It will only work till few nodes. After that, it will not. Come on, give me a good answer. Good answer. Hmm. It will depend on the height of the tree. Because you are going to put at the last leaf position. It might have to be spread to the left to the root. Now let us try why I am saying this. Now let us try to give an example. Now let us put 100 over here, 80, 70, 60, 40, 50, 65. Now let us try to, or let us try to use like this. This is a heap tree. Now I want to put a number 150. Now what I will do, I'll put a number 150 over here. Now you have to swap. How many times? From here to here. One time. Then till here. Then till here. Then till here. Because you swap 150 with 25. Then 150 with 60. Then 150 with 80. Then 150 with 100. And how many swappings you will do? One swap here. Second swap. Third swap. And fourth swap. You'll do 4 swaps. Got it? 150 with 25, one swap. Then 25 will come down, 150 will go up. Then 150 with 60, 60 will come down, 150 will go up. Then 150 with 80, 80 will come down, 150 will go there. Then 150 with 80. How many times you did? 4 times. What is the height of the tree? Was 4. Was 4 only. Now, that answers the question of one of you. How many nodes were there? Now just check it out. How many nodes were there? It was containing 2 to the power 0 nodes, 2 to the power 1, 2 square, and 2 cube. That means the number of nodes were 8 plus 4, 12, 12 plus 2, 14, 15 nodes. Did you require n by 2? No, did not require n by 2. Then how many times you required? You required, swapping you required is required 4 times. Because the 15 nodes, these 15 nodes. And you required 4 swaps, which is nothing but log of 2 of 15. Now that If this is clear, may I ask you one question? That what is the height of a heap tree containing n number of nodes? What is the height of a heap tree containing n number of nodes? Yeah, come on. Tell me answer. What is the height of a binary? Sorry, what is the height of a heap tree if there are n number of nodes? Log n, log of 2 power n. Actually, it is log n only. Plus those plus 1 plus 2 factors may not be required, because it means that if there are 15 nodes, you require 4. Now, if there are 16 nodes, you might require 4 plus 1. Now, that most of you are correct, because in that case, it could be log n, or it could be log n plus 1 also. That means, because if I add one more node, 16 nodes, it might require 5 swaps. Okay. Now, in that case, it will require 4 swaps only. Now, in this case, that means what I am trying to say at this point of time, this one is true. And what is the height of what is the height of a tree? Is log of n. It is log of n. Therefore, the swapping will take equal to 0 plus 1 plus 2 plus dot 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 up to log n. Log n only. Now, this is the actual concept, that first of all, the total time is nothing but order of 1 plus order of 1 plus order of 1 n times will give you order of n, plus swapping time is 0 plus 1 plus 2 plus dot 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 up to log of n. The total time of this will be how much? Now, in the worst case, if I take all swaps as equal to height only, that means this swapping will be nothing but log n plus log n plus log n plus log n to n times will be n log n. That means if I am going to use this one, if I am going to add all, it will be maximum of n log n. Then I take all height to be equal to log n. That means it will be on order of n log n. And what is the insertion time? Order of n. The order of n plus order of n log n will give you order of n log n. And therefore, the total time to build the heap tree as well as swapping will not be bigger than n log n. Will not be bigger than n log n. And therefore, the complexity of building a heap tree is order of n log n. In the worst case, though it will much less than this, because this I am calculating by taking all swap as equal to log n. Now you are doing n number of nodes are there, and you are going to swap every time you require maximum number of swaps, and that will require an log n times of. That means the height of the tree will not be bigger than log n, and for one node you require log n times to swap. Therefore, for n nodes you require n log n times to swap. Therefore, the total time of complexity to build the heap will be nothing, which will be given by, say, I might say, which will be given by n plus n why n? Because to insert you require order of 1 plus order of 1 plus order of 1 to n times. Will be nothing but order of n plus order of n log n to swapping. Total time will be n plus n log n, which is nothing but equal to n log n. and therefore the capacity to build a heap is N log N. Okay, till now we have covered this concept, and therefore this is the actual how to make a heap tree. The next class tomorrow we'll discuss how to convert this algorithm into a heap sort. Now, heap sort requires two steps. One, to build a heap, and the second, to convert to a sorting algorithm. Therefore, we say that this thing as build heap and heapify. The build heap is that you are going to make a heap tree, and then you are going to delete the nodes one by one so as to get a heap sort algorithm, which will require again swapping. And in the worst case, you will find that you will not require more than N log N time to perform the whole step. Okay. Now, any particular implementation of a heap tree is normally done using an array, because that requires no space wastage. Otherwise, if you are going to implement a normal tree on a heap tree, sorry, if you are going to use a normal tree and implement it as an array, you are going to waste a lot of spaces, because there will be a lot of middle in the space in the middle which will be unutilized. And therefore, heap trees are basically maintained as an array. Though I don't mean to say you can also always maintain a tree as a linked list, but to have a potential benefit, you have to use as a array only. Okay, I'll stop at this point, and if you want to ask any questions, you can ask.
Sir, in the last you said heapify and heap sort. So what is the difference between this heapify and heap sort?
No, heap sort is an algorithm. If I step where I am going to use this, where I am going to perform a swapping. Therefore, heapify is a process to swap the nodes such that the tree again converts to a heap tree. Therefore, the step what I am trying to say is, first of all, you build a tree, and then you are going to, when you are going to insert a node or even delete a node, the tree will not remain a heap tree. And then you again try to heapify it so that it remains a heap tree every time. And that is the basic concept, that the heap tree will always remains a heap tree at any point of time. Now, I'll just explain you once